So we're going to have a look at PAG 9.1, determining the rate of decomposition of hydrogen peroxide. You need two chemicals for this. Hydrogen peroxide, freshly made because it does decompose by itself, 0.167 molar, 20 millilitres of that per experiment, and this manganese 4 oxide, you're going to need 0.05 grams. The apparatus is going to be an accurate gas collection. So rather than just doing a gas collection into an upturned measuring cylinder, we're going to run it into an upturned burette. Now to see how we set this up, keep watching. You won't necessarily get this under a tap, so you need to just make sure that it's closed down here, and then you can just refill it with some distilled water. Don't have to be too accurate here on the top because, well, I'll show you. When we flip it upside down in the water with our finger on, don't worry if you get the odd bubble going to the top, because with this one, what's going to happen when we clamp it in place, we want to clamp in place so that we can see the scale facing us. We need to now let some air in until the point where the air is on the scale. It doesn't matter where, but we need to be able to take an initial reading, and we can't do that if it's full all the way to the top. The delivery tube can very carefully be placed underneath, making sure that it's well in, and then what we can do, we get ready to mix our chemicals. Let's have a look at the data that we've got. It's very important that we record our raw data in all of these PAGs. And so what we've got is just the reading on the burette as it's slowly filled with the gas. But of course, what you can see as time went on, the reading got smaller. This is not a measurement of how much gas there is, it's a measurement of how much water there is left. So what we need to do is we need to subtract each of these values from the original volume. That's going to give us the difference, or how much gas has been produced at each time interval. So there we have it. This is the amount of oxygen that has been produced each time. You see the difference between 50 and 48 is 2, so therefore it must have been 2. On something like this, which is Excel, I can always subtract from this number next to me in the field from a particular stationary number by putting $1 in front of the row and the column. So in this case it would be C5, this number, minus $C, $3. And I've put a negative in front of that so that all of these are positive numbers. Now a question that we have to ask ourselves is, do we want to use both of these runs as an average, or do we want to pick the one that looks the best, the smoothest data? And so what we're going to do is we're going to very, very quickly plot a graph of both of these. What you can see is that they are very different numbers to each other. Now, because they're very different numbers to each other, it suggests like certain small things can affect the results of this experiment. And rather than take an average of multiple runs, I think what we should do instead is take multiple runs, but then cherry pick the data that looks the smoothest. As it happens, they both look fairly smooth. They're just different from each other. So I think what I'm going to do in this particular case is, I think I'm going to calculate the end products for both of these separately to see whether or not whether the half-life of this reaction is the same, independent of the rate at which it was actually doing anything. We will find that out. So we're going to run this analysis on both of these lines. But for the sake of this video, I'll take us through this one here, the one that produced more, which is run number 1. Basically, in this PAG, I want to see how the concentration of hydrogen peroxide changes with time. So I need to know what was the concentration of the hydrogen peroxide. Now I'm going to use the amount of oxygen gas collected to tell me what the concentration of the hydrogen peroxide is. Now, let me show you how this works. First of all, we need to do a balanced equation of this reaction. So, first of all, it's going to be 2H2O2 decomposes in the presence of the manganese oxygen into 2H2O plus O2. And the very first thing to notice here is it's 2-to-1 mole ratio. It means that for every 2 of those, we're going to get 1 of those. Now, the information given about our chemical was that it was 0.167 molar, which is moles per decimeter cubed, and that so that's the concentration, and that our volume was 20 centimeters cubed. So one of the very first things we need to do is to move this volume into decimeters cubed. So we're going to divide by 1,000 and we get 0.02 decimeters cubed of this volume here. And the reason I'm going to do that is I want to find out how many moles of H2O2 have I got in my conical flask. So N equals CV, the number of moles is the concentration in moles per decimeters cubed, times the volume in decimeters cubed. So this is going to be a 0.167 times 0.02. It gives me the answer of 3.34 times 10 to the minus 3 moles. It means that in total, assuming all of it decomposes, that's how many moles in total will decompose. Now, what this will produce is half as many moles of O2. So, as a maximum, the number of moles of O2 that this could theoretically produce, assuming 100% yield, would be 3.34 times 10 to the minus 3 divided by 2, which would be 1.67. 1.67 times 10 to the minus 3 moles. So in total, I could have that many moles. Now, one thing that I now want to do is see how much volume of gas that many moles could produce. So, remembering that the formula for looking at room temperature and pressure, the number of moles would be equal to the volume, in this case in centimetres cubed, divided by the molar gas volume, which would be 24,000 in centimetres cubed. So here we can substitute in our value here, so that our volume in centimetres cubed, the maximum possible volume if all of it reacts, would be equal to N times 24,000, 1.67 times 10 to the minus 3 times 24,000. And so therefore my maximum volume is 40. I could get 40 centimetres cubed if it all goes. If 40 centimetres cubed is the most amount of gas that this reaction is going to produce, I want to find out how far along in this reaction we are, so that I can relate it to the concentration. You see, the concentration of H2O2 would be 0 when the amount of gas produced is 40. So to find out how far along in the reaction we are, what we just need to do is find out relative to the final amount of volume of gas, how much gas we have got given off. So the volume of O2 at any particular instant, if we do 40 minus that, and we divide it by 40, this will give us how far through the reaction we actually are. So for example, if we get 20 centimetres cubed, 40 minus 20 would be 20. 20 over 40 is half. It would be halfway through the reaction. At halfway through the reaction, we could work out what the concentration was of H2O2, what the concentration is with respect to the original concentration, which was 0.167. So when that is equal to a half, then we know that this here, the concentration would be half of what the concentration was to start with. That's how this works. So what I'm going to do is take the concentration by itself, the concentrations at any given point, the H2O2, I need to just multiply both sides by 0.167, 0.167 times 40 minus the volume of the O2 over 40. So of course, what's going to happen is it's going to multiply the denominator line, and so we're going to have 40 minus the volume of the O2 divided by 240. So there's the initial concentration of the H2O2 in both of these two runs. And you can see as time progresses the concentration drops. This second one, it isn't dropping by the same amount as the first one. This was a much slower reaction. Why that is, we do not know at this stage. But what we're going to do now is we're going to plot a concentration time graph with the aim of measuring half-life. Now, Desmos is a really good online program for doing that, because what it will do is it will give us the formula for the best fit exponential curve. So we'll take this over to Desmos, and then we'll try to calculate the half-life. So this is the data from that first trial. And there are two ways in which I could get to the half-life from this. What I could do in Desmos is get it to fit the very best curve through this data. And there we have it. And now what it has done is it suggested the very best values for C and B to fit my data. Now bear in mind that what C represents on this is the intercept on the y-axis, and minus B, well, B is an expression that describes how rapidly this declines. It's actually equal to minus natural log of 2 divided by the half-life. So if I take this value that it's calculated here and do the natural log of 2 divided by this, so ln2, which is 0.693, divided by 0.003187775, then I work out that the half-life is about 217 seconds. Now we can actually test this to see, does that match our data? So at what point does this get to half its original amount? And what you can see is there, it is actually 217, I got 217.44, it said 217.62, near enough. But what if? What if we haven't got the program that's going to tell us what B is? That's when we need to draw a log graph. So drawing a log graph to get to this value, 0.031, the power to which E is raised, which helps you find the half-life. We can do it with log graphs. So what we're going to do is we're going to take the natural log of all of the concentrations. So it's a time versus natural log graph. And then, so I've done it here. Now technically, you would imagine it to be a straight line, but I even want to just point out that this line isn't exactly following our data. You can see that it is shallowing out slightly. And that's actually, you can actually see that this is not exactly as straight as you'd like it. But anyway, what we're going to do here is we're now going to find the y equals mx plus c of this through linear regression. And so in doing so, this is the very best straight line through here. The gradient, of course, is equal to coefficient b, which through this is 0.031. So by doing a log concentration time graph and working out the gradient of that, then I can find the power b to which this is raised. So what have we found out? Well, we could write the rate equation. The rate is equal to 0.031, because that would be the value of K multiplied by the concentration of H2O2 here to the power 1. So here we have it. That would be the rate equation for this decomposition, and T half would be 217 seconds.